Type a contact's name and it appears the instant you finish typing out of a list of thousands. Search a giant dictionary app and the definition is just there. No waiting, no scanning. How does a computer find one item among millions, basically instantly? The secret is a data structure called a hash table. Its trick is almost magical. Instead of searching for where something is, it calculates where something is straight from the item itself. Let's build one and see. This is Logic Lab, where computer science becomes something you can see. Today, the hash table, the structure behind dictionaries, sets, caches, and database lookups. Start with the obvious approach. You have a list of items, and to find one, you check the first, then the second, then the third, scanning until you hit it. If there are 1,000,000 items, that's up to 1,000,000 checks. We've seen this before. It's linear time and it gets slow fast. But arrays have a superpower. If you know the index, jumping to slot number 42,000 is instant, one step, no scanning. So here's the dream. What if the item itself could tell us which index to look at? Then finding it would take just one jump. That's exactly what a hash function does. You hand it a key, say the word cat, and it crunches the characters into a number. For example, add up the letter values. C is 3, O is 1, T is 20, giving 24. Then wrap it to fit the table with the modulo operator. 24 mod 7 is 3. So cat belongs in slot 3. Now storing and finding are both trivial. To store cat, hash it to slot 3 and drop it there. To find cat later, hash it again, slot 3, and jump straight to it. No scanning the other slots at all. That's the constant time lookup, order 1 on average, no matter how big the table. But there's a catch. The hash squeezes a huge space of possible keys down into a few slots, so sometimes 2 different keys land on the same one. Hash dog and you also get slot 5. Hash bird, slot 5 again. 2 keys, 1 slot. That's called a collision and it's unavoidable. The classic fix is chaining. Each slot doesn't hold a single item, it holds a tiny list. When bird collides with dog at slot 5, we just add bird to that slot's little list. The slot becomes a small bucket of everything that hashed there. Lookup still works the same way. Hash the key to find the slot, then scan just that one short list, usually 1 or 2 items, not the whole table. As long as the lists stay tiny, lookups stay effectively instant. And that's the whole game, keep the lists tiny. We track the load factor, items divided by slots. When the table gets too crowded, say past 70% full, we grow it, make a bigger array and rehash everything into it. Collisions drop, speed comes back. The other half is a good hash function, one that scatters keys evenly across all the slots. A good hash spreads things out, so every bucket stays short. A bad hash clumps keys together, long chains form, and your fast hash table quietly rots back into a slow linear scan. You use hash tables constantly, probably without knowing it. Every dictionary, map, or associative array in your favorite language is one. So is every set, a structure that checks membership instantly and removes duplicates in one pass. Database indexes use them to find rows in an instant. Caches use them to remember recent answers. Compilers use them to track variable names. Anywhere you need to ask, where is this thing? Right now, a hash table is probably the answer. Recap: a hash function turns a key into a slot index, so you compute a location instead of searching for it, constant time on average. Collisions are handled by chaining each slot into a tiny list. Keep those lists short with a good hash and by resizing when the table fills up. Hash tables are blindingly fast, but they have a weakness. They can't tell you what comes next in order or give you a sorted range. For that, you need a structure that stays balanced as it grows, a tree. How to keep search fast as your data grows, next on Logic Lab. See you there.